message you. Before we get into some real system design problems, let's first understand how to actually approach system design interview problems, and generally what you can expect in a real interview setting. Of course, system design interviews are about taking real-world problems and breaking them down and designing the core functionality of these systems. Of course, since we're dealing with technical problems related to computers and the internet, we can expect that every design is going to have some commonalities. Things like servers. Of course, we're going to need to have some application running on some server. We can expect that if we need to scale these up, we're going to have multiple servers. Now, how do we route traffic to multiple servers? Well, we have our friend, the load balancer. What if we need to store some data? Well, we could have some type of database, and all these servers will be reading data from that database and writing data to that database as well. Now, this sort of very high-level design is a good start, but it's pretty hand-wavy. We haven't talked exactly what we're going to do. I mean, this sort of design will apply to every single design problem, and your interviewer wants to know more than you know what a server and database and a load balancer are, right? This is a good start, but it's not quite enough. We do generally need to dig down a bit more into the details. What is the schema of the data that we're using? Are we using SQL or no SQL? How are we handling the scale? Do we even need to handle any scale with the database? Maybe just a regular SQL single instance DB is enough. It depends on the problem, of course. It's pretty common to be given a really open-ended problem for system design, something like design Twitter or YouTube or WhatsApp. And of course, it's impossible for us to cover this in typically a 45-minute interview. If Twitter were really that simple, anyone could build it in 45 minutes, or at least design it and then implement it relatively quickly. It's not that simple. It takes hundreds and thousands of engineers to actually do this. So typically, we are tasked with designing a small piece of Twitter, something like the Twitter feed, or maybe Twitter messaging, or maybe just the like functionality. When you click that heart like button on a tweet, maybe we're just designing this single feature, because I bet it took dozens or hundreds of design document pages to design even just a simple feature like that. So our job in the system design interview is to break it down. We need to dig into the problem statement like design Twitter. We need to clarify with the interviewer, well, what functionality are we focusing on? Are we just designing a particular feature, or maybe the high-level design just for the general site itself? But in that case, we probably would not be digging too far into the details. But what I'm getting at is that it's all about scoping out the problem with your interviewer. This is not something you can do yourself, because your interviewer is ultimately the one guiding you. They're sort of like your client, and you're the one designing something that meets their requirements. That's a good way to think about it. And when it comes to scoping and really understanding the requirements of the problem, we can typically categorize the requirements in two buckets. One is functional requirements. These are the actual features that we're implementing. Like, how do we want the design to actually function? How do we want the application to function? What do we want to happen when we like a tweet? Are we allowed to like a tweet multiple times? Probably not. A single user should not be able to like a tweet multiple times. So every time somebody likes a tweet, we should store their user ID in a database so that we kind of remember that, right? This is a very high-level scenario, but this gives you the general idea. Also, we want to know which features. We're talking about the like feature here. Maybe we don't even care about the like feature. Maybe we just care about the news feed feature, where we see a bunch of tweets and we can scroll through them. And every single user is going to have their own unique news feed that we need to generate. Maybe that's the functionality that we're trying to build. But it depends. You can see that this gets very open-ended, and of course that's why we need to clarify this with our interviewer, because first of all, they already have something in mind. They probably have a small piece that they want to focus on as well, but at the same time, they're looking to see if you clarify in general, because that's a very important thing on the real job. Imagine if you designed a very large feature or application and it turned out to be the wrong one. It didn't meet the actual requirements that we wanted to implement. It was the wrong feature that we did. That's a very expensive mistake, and that's something we try to avoid when we are actually designing systems. And one thing your interviewer is looking for is to see how careful you are, or if you just make assumptions without actually clarifying what we're trying to do. That's a mistake to avoid. You don't want to just jump straight into the design and start solving the problem, and it turns out you solved the wrong problem. Non-functional requirements are pretty much everything that is not about the functionality of the application, namely things around scalability. Any YouTube tutorial can teach you how to build a Twitter Twitter clone. But first of all, it won't have all of the features and functionality that real Twitter does. And second of all, it definitely will not be able to handle the scale of real Twitter. Maybe a tutorial will teach you how to store Twitter posts in a regular SQL database, and you just have a single instance database. Well, this definitely is not going to scale to hundreds of millions of users, which is the traffic that Twitter actually handles. So we need to understand what type of scale are we handling. Possibly we're going to have 100 million daily active users. Maybe that's what your interviewer tells you. And so you need to design around this requirement in mind. And typically these non-functional requirements are the difficult part of system design interviews. Handling a large amount of scale is one problem. When it comes to scalability, we could have other things that fall into it. Things like throughput, which is sort of like 100 million daily active users. That kind of falls into throughput. We may have hundreds of thousands of requests hitting the database per second. Maybe we also want to know what the storage capacity is, because if we have hundreds of millions of users, first of all, we're going to have a lot of requests going to our database. That's throughput, but we're also going to need to store a massive amount of data. A single instance database theoretically can work, but even just a single query on that much data is going to go very, very slow. It could take seconds. It could take 10 seconds. It's going to be really, really slow. So first we need to understand, how do we even store that data itself? And another set of non-functional requirements comes from the performance. So when we talk about performance, of course, latency is a big one. We want the performance of our application to typically be faster rather than slower. So we want queries to our database to be as fast as possible. We would have to partition this database for the read-write latency to be lower. And then of course, that will be directly impacting users as well, because they'll be the ones having to wait for these requests and queries to actually complete. So latency is important, but maybe we only care about a subset of latency. Maybe we want the reads to be faster. We want reads to be less than 1 second. So every read should be less than a second, but maybe we have more tolerance for slower writes. Maybe writes can be slower. Maybe they can be 2 seconds or 3 seconds or something like that. Also, when it comes to performance, availability is pretty important for Twitter. So imagine if somebody opens up Twitter and they try to get their news feed, but they get an error message. Their internet is working completely fine, but maybe something went wrong with the database, or maybe something went wrong with one of our servers. One of our servers crashed and then the user did not get the correct response. This could sort of fall into scalability as well if it's a scaling related issue. But in general, we think of availability as the number of requests is the denominator, and the numerator is the number of non-error responses that we get. So the total number of non-error responsive divided by the number of total requests gives us generally the availability, and we want this to be as high as possible. Maybe we want 99% or maybe 99.9%. This is the percentage of requests that will not return an error. So of course we want it to be as high as possible, but it's impossible to have 100% availability, so you'll have to meet your interviewer somewhere in the middle. What's the availability that we're looking for? Because maybe we can actually design a system that will have 100 nines of availability, like 9999999. But as we learned earlier, 5 nines of availability is something like 20 or 30 minutes of downtime per year. So getting that even lower isn't a huge issue. Like if Twitter goes down for 20 minutes per year, that's not the end of the world. I think we can even add another 9 and get down to somewhere like 5 minutes. That's really not the end of the world. Maybe we can spend a lot more resources and get this down even lower. Maybe we can cut this to 1 minute or 10 seconds, but the improvement from that might not be worth the cost. So these are trade-offs that we're going to have to make. We definitely don't want to over-engineer our solution. We can't have a perfect design. Our goal is to meet as many requirements as possible, and when we can't meet every requirement, we have to make intelligent trade-offs. We have to sacrifice something that's not super important to gain the core functionality that we're actually looking for. Now, when it comes to actually quantifying a lot of these metrics and requirements that we're trying to meet, in an interview setting, you don't have time to actually get the exact value that you're looking for, like the exact throughput, and to calculate a lot of these metrics. So what we do to get around that and to have a shortcut is to do something called back of the envelope calculations. They're called that because you do them on hand, like on the back of an envelope or maybe on a napkin or something, but you don't need a calculator to do these. You can do them in your head at a high level. Let me give you a quick example, and then we'll talk about some numbers that you should generally be familiar with. Let's say we know that Twitter has 100 million daily active users, and let's say among these 100 million people, each of them reads about, let's say, 100 tweets per day. But maybe for writing a tweet, on average, only a tenth of these people make a tweet per day. So for each person, we have 0.1 tweets. So how many tweets total do we expect to be written? Probably 10 million writes per day. So 10 million write tweets. Now, if each person is reading 100 million tweets, we'll have about 10 billion reads. So I'm gonna change this 0 to a B. Sorry if it's not super readable, but we have 10 billion reads per day and 10 million writes. So a quick calculation for throughput for reads and writes. How many reads do we expect per second? Well, we take 10 billion and divide it by the number of seconds in a day. How do we get the number of seconds in a day? Well, you can probably memorize it, or you can kind of do the quick calculation. I'll go through that really quickly. We know there's 60 seconds in a minute. We know that there's 60 minutes in an hour. We know that there's 24 hours in a day. So you can actually multiply this out if you're decent enough at math. This is 3,600, 60 times 60. You know that because 6 times 6 is 36. And we kind of add these two zeros together, and then multiplying that by 24. Well, multiplying this by 10 would be 36,000. Multiplying it by 20 would be 72,000. And then 3,600 times 4 is going to be something like 14,000. So this is going to end up being something like 86,000. But I went through that exercise just to kind of show you that you can roughly approximate this to be 100,000, and that would be perfectly good enough. I mean, if you were off by a factor of 2, like if you had this doubled and this was 160,000, or if you were off by a factor of 2 in the other direction where you approximated this to be 40 or 50,000, you would be fine. It's not a big deal to be off by that much. So in this case, our denominator, the number of seconds in a day, is going to be 100K, 100,000. So at this point, you can probably figure out how to do this in your head, or at the very least write these two numbers out and then just kind of cross out the zeros. 100,000 has 5 zeros and 10 billion has 10 zeros. So we would end up with a number with 5 zeros, which is 100,000. So we expect 100,000 reads per second, which is definitely a large number. Now, if we were actually doing this with 10 million, we would basically just remove 3 of the zeros, because we know 10 million has 3 less zeros than 10 billion. So in terms of writes, we need to be able to handle 100 writes per second. Now, when it comes to these high-level designs and these applications that we're trying to design, like Twitter, for example, there's a lot of auxiliary services. Our application may need to handle things like authentication and things like payments, and there's a lot of kind of core functionality that a lot of applications have. Unless the whole problem that you're trying to solve is handle authentication or payments, you can typically ignore these. Like if we were designing the Twitter feed, we wouldn't have to talk about authentication. We would have to talk about the concept of users and user IDs to uniquely identify people, but not with how they're actually logging in and logging out, or how they would maybe pay for services and things like that. But if you're unsure, you can always clarify this with your interviewer. Now, really quickly, I wanted to go over some really basic numbers that you probably already know. Things like 1 second is just a second. A second can get into a smaller unit like a millisecond. A millisecond is just a second divided by 1,000. And then we get to another smaller unit, microseconds. This is the unit. It's actually a Greek letter. It kind of looks like a U, but a microsecond is 1/1,000,000 of a second. So 1 second divided by 1,000,000. And then we have nanoseconds. 1 ns, a nanosecond, is 1 second divided by 1,000,000,000. So that's typically as small as we get to. And then we have bigger numbers. 1 second can get to 1 minute. We know, of course, that just has 60 seconds. And we can get to 1 hour, which has 60 minutes. And then we can get to a day, which has 24 hours. When it comes to storage, we're talking about bytes. And then we can get up to kilobytes, which kilo means 1,000 bytes. We get to a megabyte, 1,000,000 bytes. We get to gigabytes, 1,000,000,000 bytes. This is what we typically use for storage, at least persistent storage. And then we get to a terabyte, which just adds 3 more zeros. Instead of billion, we have a trillion. And then then we get to a petabyte. Usually this is as big as you need to go. So this is 15 zeros. So 10 to the power of 15, a petabyte of data. Quite a large amount of data. You typically won't go past this unit because you can have 1,000 petabytes or 10,000 or 100,000, and you don't really need to know the unit above that. So that's the good part. You don't need to memorize any units beyond this. Now lastly, I wanted to show you this site that I did not create. This is actually based off of some numbers that Jeff Dean talked about. Jeff Dean works at Google. He's actually responsible for a lot of solved problems in the distributed system space. And these are some latency numbers he talked about a decade ago. But let's take this scroller and move it all the way to the right because this is updated as of 2020. So these are some common latency numbers. You don't have to memorize them by heart, but you should generally have a high level idea of how these work. Like we know L1 cache is pretty quick. It's a nanosecond, but of course we know that main memory is slower than CPU caches and things like that. So referencing memory is about 100 nanoseconds. Again, you don't need to memorize that exact number, but you should know that memory is a lot slower than cache. And of course we have disk. So SSD reads are a lot slower than memory. It looks like about 100 times slower. And of course we know that sending data over a network is even slower than reading from disk. You can see 500 microseconds compared to 16 microseconds for an SSD, and that's actually in the same data center. Sending data over the internet all around the world is even slower. Here you can see it's 150 milliseconds for a round trip from California to the Netherlands. And you can read this and get a decent idea. This is not created by me, it's created by Colin Scott. You can see the URL above. Feel free to check it out. But again, don't need to memorize all this. Just have a decent conceptual idea of what's faster and what's slower, and generally by how much. So we talked about a lot of things. The only thing left you need to understand before getting into the system design practice problems is have a general high-level overview of distributed systems and system design. I covered that in my system design for beginners course, so if you haven't checked that out, I highly recommend it. Or maybe if you already are familiar with distributed systems, you can skip that. But anyways, let's get started now. Okay, let's design a rate limiter. So even though most developers are familiar with what a rate limiter is, let's still briefly go over the background of what we're trying to do here. Let's say you have a 4-digit password on your phone. If you get the password wrong, you only have a limited number of retries. Let's say 3 retries per hour or something like that, and then you get locked out. This is one of the simplest forms of a rate limiter. Now, in this context, can you tell me what is the rate limiter accomplishing? Why do we even have it here? Are we trying to save money? Like, are we trying to save resources on our phone? Probably not. We're doing this for security reasons. If it's just a short password like this, we could brute force it, and if the FBI gets your phone, they'll be able to crack it relatively quickly, even without using anything super crazy. Like, even a little kid could actually crack it if they just kept retrying, random passwords. If you try to upload videos to YouTube and you try to upload, I think, over 20 videos in a 24-hour period, you won't be able to do more than 20 videos. You'll have to wait 24 hours until you can do that again. Why do you think YouTube does this? This is probably not for security reasons. I mean, they don't care how many videos you upload. It's not going to do anything. Well, first of all, YouTube is running a business, so cost with videos can be pretty high. That's a lot of data you're storing. In theory, someone could upload, an infinite number of videos, and that would take up all of YouTube's storage. That would not only cost a lot, but it would actually also crash YouTube potentially, maybe take up all the storage for everybody else. So this is also an availability issue. So rate limiting is clearly very important, and it's important to get it right, but the context also matters. Let's say that, staying on the subject of YouTube, what about people who are making comments on videos? What if I try to make 1 million comments in a day, and I just go on a bunch of popular videos and make 1 million comments? Is there a reason that this shouldn't be allowed? Well, if you've been on YouTube recently, you may have seen a lot of bots in the comments. So this can kind of be a user experience issue and security issue as well. You wouldn't want someone to just be able to have infinite control over something as big and powerful as YouTube. But my question is, should comments have the exact same limit rule as uploading videos? Because an application like YouTube could have rate limits in many places. Should we just have a single rule like 20 videos per day? So in this case, we'd have 20 comments per day? Well, sometimes context matters. Maybe with comments, we can actually allow people to make 100 comments per day. Overall, the main goal that we're we're trying to achieve here is to prevent users or possibly even bots from making too many requests in some time period. So that's the background here. So the first step of the interview would be to clarify the functional requirements with your interviewer, because as we kind of discussed, rate limiting can be really open-ended. Of course, in a 45-minute video, we can't cover every single possible case and dive into some of the details as well. Even if we just focus on a single example like the YouTube case, we still wouldn't be able to cover everything that YouTube implements. So this is mainly about us getting a picture of the high level that we're trying to accomplish and being able to discuss some of the details, not every detail. That's, not possible. We try to focus on the most important details. The first question I would personally ask is, are we designing a rate limiter for some back-end API? In my experience, that's, most commonly where rate limiters are implemented, especially in distributed systems. And suppose the answer is yes, that's what the rate limiter is supposed to protect, some APIs that we have. My next question would be, is it just for a single API? Like maybe just a single microservice that we own and we are trying to protect just this single microservice? Now, most likely the answer would be no, but the reason I even entertain this thought is because the easiest way we could actually do a rate limiter is inside of the application. Like in the microservice, we could add more code to that and implement rate limiting in the code, like in a hash map, for example, just keeping track of our rules in the code itself and then keeping track of the requests in some kind of memory data structure like a hash map. Most likely the answer would be no, though, because this is not so much of a distributed systems problem. So let's say we're trying to design this rate limiter such that it will be able to protect multiple microservices or APIs, and it should be reusable so that it can protect multiple APIs, so that we have to implement that rate limiter as a separate service. Now, a subtle point here is that each of these APIs, for example, maybe there is a separate uploading API, like just thinking in context of YouTube, and there's a separate comments API. I'm not saying this is the case, but if this were the case, each service here is not going to be a single instance, API. There could be multiple instances of the upload API, but both of these need to be able to communicate with the same rate limiting service. These need to be in sync. That's another reason why we can't implement the rate limiting inside each of these instances, because suppose I upload one video, I end up hitting this service over here, the first one. I upload a second video, I end up hitting this service over here. So I could, in theory, bypass the rate limiter by, accidentally hitting other instances of the APIs. That's why we can't implement it at the API level. We have to implement it at, some kind of shared service like the rate limiter, so that this rate limiter will know I've uploaded 2 videos, whereas each of these will think I uploaded 1 each. Now, suppose requests are hitting the rate limiter and the limit has been reached. What should happen at that point? Well, we should not allow any more requests. In general, for a valid request, the rate limiter will allow the APIs to fulfill the request. But in the event that the rate limit has been reached, the rate limiter should not allow the APIs to actually fulfill the request and just tell the user that they are being throttled, that they cannot, continue to send requests because the rate limit has been reached. And to be even more helpful, we could let them know what is that time period. Maybe it's 24 hours, just wait this much longer until you send another request. And in the context of HTTP, this would be a 400 error because it's a client error. There's nothing wrong with our servers. They're functioning completely fine. It's just that the client is sending too many requests, so they are being throttled now. And specifically, the error code for rate limiting is actually 429. This is one of the more popular HTTP 400 codes, but I don't think you necessarily would need to memorize it. Just based on your experience, you might be familiar with it though. I think another thing that's worth mentioning is, what about client-side rate limiting? Because that's also really easy to implement. In some client-side code, maybe JavaScript, or maybe it's a mobile application, we could have some code that doesn't even send the request in the first place. This would be ideal because it's really simple and easy to implement, and we probably should have client-side code that does that anyway. But can you tell me what's a problem with this approach? approach? This is a question I would personally ask a candidate because it's such a basic question, but it's also really important. What would happen if we didn't have a rate limiter in the first place? We just implemented it client side. Well, in theory, the user could be able to reverse engineer API requests and continue to send those. They might not even be using our application in the first place. We have some public API endpoint. They can hit it just by themselves, maybe with a curl request. And that would be such a simple way to bypass the rate limit. And if YouTube didn't have a rate limiter like this, you can imagine, YouTube would have already crashed by now. Somebody would have taken it down. So it's very important in many cases to have a real rate limiter. Now, a last functional requirement I want to go over is how do we actually identify users? Well, it would kind of depend on the context of our application. Like, are we just going to use the user ID? Like, do users actually have to sign up before they send a request? What if that's not the case? What if a user does not even have a user ID? On YouTube, that doesn't make a lot of sense because you do have to have an account to
सामने वाली अच्छा अच्छा अब देखो बेटा अपनी माँ बेंगलोर चली गई थी उसके बाद से वो लास्ट किटी थी बेटा क्या है बेटा माँ की बेटा क्या थी पूरी किटी पार्टी में जितनी महिलाएं थी ना उम्र में सबसे छोटी और सब लोग मतलब माँ की बात मानते थे वो बहुत न्यूट्रल बात करती थी हैं तो सभी लोग मतलब बेटा देखो माँ की एक अलग वो थी हैं
क्या बेहतर आप बताओ तो मालूम है क्या
वो किसी के 3-5 दिन बिल्कुल पता नहीं
वो वाला नहीं है नॉर्मल रिमोट वाला है और बस
और
अच्छा और ये स्विच बोर्ड लगाने का कितना बोल रहा है स्विच हम ला के देंगे मटेरियल तो
10-11 साल चलिए ज़्यादा और वो देखो वो तुम्हारे उसमें नया छोटी वाली आई थी
नहीं तो पर स्विच कितना लेगा
हैं बेटा
900 में तो इंक्लूडिंग मटेरियल बोल रहा था एक दूसरा वाला स्विच बोर्ड के साथ तो मटेरियल तो हम ही ला के दे रहे हैं ना स्विच बोर्ड वगैरह
अलग बहुत अलग में इसकी बेटा
अच्छा ठीक
मोटा बहुत खराब नॉर्मल है
कल गीजर वगैरह को फिटिंग करनी है भैया थोड़ा वो मतलब किचन में जो रहेगा ना गीजर भी ला के ले आऊँगा और 2-3 वो बाथरूम के हैंडल रहेंगे
हाँ सब अपडेट चाहते हैं गीजर होना चाहिए पानी का होना चाहिए
ठीक है फिर बाथरूम के गीजर तो चार लगा देते हैं
तो अपनी प्लांट पे रखा तो है लगा तो वो नहीं वहाँ के लिए
ठीक है वो तो एक बार सफाई करवानी पड़ती है और ये ऊपर सोलर वगैरह आप कनेक्ट करोगे कौन करेगा यार एक बार चेक करवा दो वो सोलर वोलर चल भी रहा है कि नहीं नहीं तो वो चेंज कर दिया ना उनने ऊपर, अब वो रिप्लेस किया कि चेंज किया, रिपेयर किया, समझ में नहीं आ रहा ना, इसलिए मेरे को टेस्ट कर। नहीं तो ऊपर चेंज हो गया है वो। नहीं तो आप एक बार चालू करके बता देना ना उसमें, और वो उसमें पाइप वाइप कनेक्ट कर दो आप। अरे सोलर वोलर तो बिल्डर ही ला के दे रहा है ना, बिल्डर ने बोला है लगा के देगा सोलर वोलर। क्या लगेगा आप बता देना कौन सा स्विच है। ठीक है आप बता देना लिख के, वो IBO है ना होलसेल, वहाँ से ले।
अभी तो बेटा गर्मी में थे ना,
कल एक्चुअली गीजर चालू करना लगाना, थोड़ा ये प्लेट वेट वो लगा दीजिए थोड़ा जल्दी, ठीक है।
सोलर का तो चाहिए कि वो जब सुबह सुबह एकदम सुबह निकालो तो आता है, बीच में ओपन करना होता है ना तब नहीं आता।
Upload and comment, but in other sites it could. So we probably want our rate limiter to be general enough, since it's going to be serving many possible APIs and many possible applications. Like maybe Google implements a rate limiter, they want it to not only serve YouTube but also serve Google search. So we want to make it as general as possible in this case. So we should be able to support many IDs. We can even use like an IP address. That would be the most general thing to use. But let's also say that we're not going to focus on a particular case, because there could be trade-offs with IP address if we're talking about YouTube or something like that, but we're not going to get into those details. We're just designing a general rate limiting service that could be used in many contexts. Okay, next let's talk about the non-functional requirement. This is more about things like performance, not like what our rate limiter should do, but how well it should perform, how it should do what it's doing basically. Because think about it, with every request that the user makes now, with a rate limiter sitting in between or being involved in that request, isn't it going to slow down the request? Because every request has extra overhead now. So I would ask about the latency requirements, but I would already think that we want latency to be as low as possible, because we don't want to add another 1 second to every request now just because we have a rate limiter. We want to pretend like the rate limiter doesn't even exist. And latency is probably the most important non-functional requirement in this context. It's also worth talking about throughput. If we have a rate limiter that is being used by a lot of services, in theory it should be able to handle a lot of throughput. I won't try to quantify this, but in general this means that we should try to design it such that it is scalable, so horizontally scalable, like we can continue to add resources and our rate limiter should be able to handle that. Another important one is storage. What are we going to be storing? How much are we going to be storing? So first of all, we have rate limit rules. We talked about how a single application can have multiple rules, but we're also dealing with potentially multiple applications, and all of them will have their own rules. But this is really not the bottleneck. Do you think a single application like YouTube, how many rate limit rules can it possibly have? 10, 100, 1,000? Well, there's not that many features on YouTube. It's not like there's a million different features, so we probably don't need a large number of rate limit rules for a single application. So we probably don't even have to kind of worry about the rules part being a bottleneck. What about the number of users that we're serving? Because think about it, in our rate limiter service, for every single user, we have to identify them, let's suppose an IP address. So this is kind of going to be the key that identifies a user, and then for that user, we're going to have to map them to possibly the number of requests that they've made so far, so that we know, should we throttle them or should we allow their request to go through? So how much data would we end up storing for each user? Well, just at a very high level, without even knowing what we're going to be designing here, an IP address has 4 bytes, and let's say to store the number of requests that they've made in some time period takes 128 bytes. I'm just kind of overestimating, and we don't even know what our design is so far, but let's just say these are the numbers that we're given. So for each user, we have potentially 132 bytes, and for a really large application, let's think we have a billion users that we're working with, so we have potentially 132 billion bytes. That's 132 gigabytes. By the way, this is something I think you should be able to know mathematically. A billion, remember, is giga. So this is the amount of data that we need to possibly store for the actual rate limit, the counts for each user itself, not the rules, but this. Spoiler alert, 132 gigabytes, it's feasible to fit this into memory, and that's kind of the main takeaway from this portion. Now, the last non-functional requirement I want to mention is availability. Now, in theory, our rate limiter should be as available as possible, like the highest degree, 5 nines of availability. But a question I have for you is, what if our rate limiter goes down? How should our application handle that? There's a couple terms called fail open means that if something in our system goes down, our entire system, including the APIs, should function as if the rate limiter never existed. Fail closed means that if one part of our system goes down, the whole system will basically go down. We will tell a user, well, we have a server error, a 500 error, we can't do this, so we're not going to allow any requests. My question to you would be, which one of these makes more sense in the context of a rate limiter? Should we fail open or fail closed? Well, if we fail open, then most users will still be able to use YouTube, for example. Most users will still be able to use the app normally, but a small subset of users, possibly, who are trying to abuse the app will also be able to get through. In the context of YouTube, it might be okay for a small portion of time. Maybe the rate limiter only goes down for like 5 minutes or something, and people were able to, spam comments or something like that. Probably not the end of the world. But if we fail closed, then we take down the entire system. Users can't make any requests, so this would affect all 1 billion of our users. Depending on the application, we probably would choose to fail open, but I'm just discussing this to kind of give you the main idea here, because that's what system design is about, talking about these types of trade-offs and these types of problems in the context that they are involved in. I think most likely, though, availability wouldn't be a big part of your rate limiter interview. Now, to wrap up the non-functional requirements, I want to say, even though we spent a bit of extra time on it, in general, you should aim to get all the requirements from your interviewer within 5 to 10 minutes. Though throughout the interview, you can continue to ask your interviewer clarifying questions about small details. But the reason we do this at the beginning of the interview and not at the end is because if you don't even have the correct requirements, you're going to end up creating the wrong design, and then by the end of the interview, you won't be able to have time to rework your entire design. So you want to at least have the big requirements clarified at the beginning. So next, let's propose our high-level design to make sure that we have the general picture of the problem correct. And after we've done that, then we can kind of dive into the details. So first, suppose when a user makes a request, the first thing that they hit is our rate limiter service. So it kind of serves as a reverse proxy, because this obviously is not going to have our application logic like our APIs. This is going to decide whether we should allow the request to our APIs, and then the API can fulfill that request, or we should not send the request to the API in the first place, because the whole point is to not overload the APIs, even though deciding whether we should rate limit or not should be as fast as possible. Next, we need to have some type of storage to store all of our rules. And these are not defined by the user, of course, these are defined by us as developers for our particular APIs. Like YouTube can't upload more than 20 videos in 24 hours. We have to store that somewhere, and of course this has to be persistent. I mean, we might change it later, we might allow even more uploads per 24 hours, but we definitely don't want this rule to be deleted, so it should be persistent, most likely in a database, whether it's SQL or NoSQL. Probably doesn't matter, because remember, the scale of our database doesn't matter. We're not going to be storing that many rules, maybe 1 million, maybe 1 billion. It's not really that big of a number, but probably not 1 billion. Now, the rate limiter is mainly going to be reading these rules. So suppose a user is trying to upload a video, the rate limiter will check the rule for uploading videos and check, oh, okay, they can only upload 20 videos per 24 hours. Now, how does the rate limiter know how many videos the user has uploaded in the last 24 hours? Well, we could have an in-memory key value store, something like Redis or Memcache. And one of the reasons we would do this is because the rate limiter is not only going to be reading from this, but it's also going to be writing. So suppose a user uploads uploads a video for the first time, then the rate limiter, of course, is going to say, well, this user has uploaded one video in the last 24 hours. We actually have to write to this, and we want it to be as quick as possible. We know writes typically take longer than reads, and we know that memory is definitely faster than persistent storage like disk. And we know that most likely the amount of data that we're going to be storing can probably fit into memory. And then lastly, let's say that we have, a bunch of APIs. I'm kind of drawing them like this, but you can have many different APIs, and the rate limiter will be the one deciding where to forward the request to and whether it should do that at all. In the case that the request is allowed, when we would know that from reading the key value store, we forward the request to the API, and then the API will fulfill the request through the rate limiter and send it back to the client. In the case that we can't do this, we would just send a response to the client that they've been rate limited 429 code, and our APIs would never even know that the user made the request in the first place. So most likely, as you talk through your high-level design, you will kind of be getting some feedback from your interviewer, like proposing a database for storing the rules. Having some type of rate limiter in between the user and the actual APIs is just one approach. We could have actually just sent the request to the API itself, and then the API actually has, maybe application logic to read from the key value store directly, and maybe in that case we don't even need to have rules in the first place. But remember, we're trying to design this to be as open-ended as possible, to be as reusable as possible. Now let's dig into some of the details. And probably the most important detail is, what type of algorithm are we actually going to use for rate limiting? Of course, we're going to have some type of limit, like 100 requests per minute, for example. This is a rule, but what exactly does that mean? Suppose we have a timeline like this at the 1 minute mark, and maybe this 1 minute time point means 12:01, and this means 12:02, this means 12:03, etc., etc. So we actually have some type of clock that kind of designates our time windows, right? Like we have 1 minute, we're saying 100 requests per minute. One very simple algorithm we could do is based on the clock, like every 1 minute time period, we only allow at most 100 requests. So somewhere in here, we will have 100 requests at most. And then when the next minute starts, based on the clock that we're using, we will allow another 100 requests. Now, in theory here, a user, right before the minute is ending, right before it hits 12:02, a user could send 100 requests, and then 100 requests. Now, in theory here, a user, right before the minute is ending, right before it hits 12:02, a user could send 100 requests. And then right after it hits 12:02, there's a brand new minute there, they can send another 100 requests. So then here, they can send another 100 requests. So in the span possibly of 2 seconds, they were able to send 200 requests. That kind of just broke our rate limiting rule here. Now, obviously this is a problem, but it may not be a huge problem, because yeah, they sent 200 requests in 2 seconds, but now they have to wait, maybe 59 more seconds until they can send another 100 requests. So maybe over a long period of time, our rate limiter will be pretty accurate, but maybe we don't want these types of spikes in the first place. But before I get to how we can kind of fix this and use a possibly better algorithm, the benefit of this algorithm, which is called the fixed window algorithm for rate limiting, because each window is fixed. Like this is a window based on our clock, we are defining that as a window, and this is a window, and this is a window. When the minute ends, we get a brand new window. The benefit of this is, since we're storing these counts and we're storing them inside of the key value store in our memory, this is a pretty simplistic approach to take. We don't have to keep track of exactly when each request was made. Like maybe, 50 requests were made over here, 50 requests were made over here. We don't care exactly what time they happened. We just care that they happened in this minute. We don't care about the second that they happened. And that would be very simple to store in our key value store, because we would only need to include the minute for all 100 of those requests, and the count of them, which is suppose 100. So that's the benefit. But what do you think would be a better algorithm that would be more accurate? Well, it's called the sliding window. You might have heard of it. And just like how it sounds, we would be much more accurate in that anytime a user makes a request, suppose a user makes a request over here right before that minute is over, of course we would look at the last 60 seconds. But if a user is making a request at the next minute, unlike the sliding window where we just disregard everything that happened before this minute, we actually include this and still the last 60 seconds. So maybe up until this point. So this is the last 60 seconds. So every time a second passes, we shift our window over by 1. So if there were 10 requests happening over here, by the time we get to this point, we disregard those. We do not include those in our total. Now, obviously, this is much more accurate. It will actually pretty much always enforce this 100 requests per minute rule. But the downside here is that we will actually have to store the exact timestamp that that request occurred. I mean, maybe we can just do it based on seconds. Now, we can store it using a Unix timestamp to be accurate, but each timestamp is going to be 32 bits or 4 bytes, and that's not a big deal. But we're gonna have to do that for every single request. We're gonna need to know the exact time for every single request. So 100 requests is gonna end up with 400 bytes per user, and that could get even higher depending on what type of rate limit rule that we are using. So that's kind of the trade-off here. Even though the fixed window is less accurate, it is less cost intensive, and the sliding window, though, is much more accurate, it requires much more resources and is more complex to implement, because as our rate limiter reads from the key value store, we would only be reading the last 60 seconds using that sliding window, and then possibly we would delete the rest of the data that is stored at that time, at the time that we actually read from it. And deleting that would save us some space, but still another operation that we'd have to do. Now, in terms of implementation with Redis, this can be accomplished with sorted sets. Even though it's a key value store, you can still map a single key to a set of values in sorted order. You know, we'd probably sort it based on timestamp, of course. And there are actually many more algorithms when it comes to rate limiting. I personally think it's more of a domain knowledge topic, and I wouldn't expect someone to know, all of them and be able to describe them in detail. Some that we didn't talk about, but you can research, are token bucket, which instead of using windows, uses the concept of a refill rate, and also the sliding window counter, which can actually be a balance between the fixed window and the sliding window that we talked about. But again, I really don't think you would know this in detail unless you have some specific domain knowledge in that, or of course, you're studying for system design interviews. But I think even being able to talk about some of the trade-offs that we did would be more than enough, but that's my opinion. Now let's talk a bit about the actual data schemas we would use for the in-memory store. It's pretty simple. We would have some type of key, possibly the user ID or IP address, and we'd map it using maybe the fixed window algorithm. We would map it to some count. That's very straightforward. And then the rate limiter would enforce that count using whatever rule that we have defined. And when a user makes a request, what do we do with that count? We increment it plus plus, but suppose that this count applies to 12:01, and when the next minute starts, we want to reset the count. Well, with Redis, we can actually do this pretty easily with an expire. You can set data in Redis to expire, so it will kind of automatically clean this up for us, and then we will have a reset count to 0. We will then start incrementing again. That's another reason why the fixed window algorithm is so easy to implement. It will kind of reset itself. We don't have to keep track of the timestamps. We can set it to expire every 60 seconds, or expire, exactly at 12:02. Talking about the database schema is also not super complicated. Every rule needs an ID to be able to identify that rule. Like when a request hits the rate limiter, maybe for uploading a YouTube video, the rate limiter needs to be able to find that particular rule for uploading YouTube videos. So this ID would be a string. The rate limiter might also need to know which API it should forward the request to. So maybe some type of way to identify which API this rule corresponds to, and also maybe which type of operation, I'm just using OP for short, but what type of endpoint or operation are we going to hit on that API? Are we going to upload a video? Are we going to comment? Are we going to do something else? We would also, of course, want to store the time unit that this corresponds to. Could be a minute, a second, an hour. Depending on how we implement this, we could also, store this as a string, and the rate limiter will be the one responsible for interpreting that string, deciding is it a second, a minute, and all that. And we will also want to store the number of requests allowed. So that will be likely an integer. So take an example for this. We talked about 100 requests per minute. So this 100 would be stored in this entry, and a minute would be stored in the time unit entry. entry. So that's more or less the design of a rate limiter. We touched on a lot of the key components, but depending on your interview and your interviewer, this could be open-ended. It could go in many different directions, and you may be able to focus on different aspects of it based on your experience. There's a couple more points that I wanted to make. When it comes to scaling the in-memory store, if we needed to store, terabytes of data in memory, we would probably have multiple instances of an in-memory store. We would need to scale these horizontally. But of course, a user should be able to access the same data every single time. If we have our in-memory store and we sharded it, for example, like we have half the data stored here and half the data stored here, if this user's data is stored on the second in-memory store, they should be able to hit that one every single time. What algorithm could we use to accomplish this? Probably consistent hashing, though I won't get too into the details because I don't think that's the main component of a rate limiter. We kind of talked about a lot of parts, though maybe your interviewer will want to explore this part a bit more. But there's also another bottleneck that I wanted to talk about, and that has to do with the latency of our requests. We want to minimize the latency. We want it to be as low as possible. Of course, reading and writing to memory, we can't really do much better than that, but what about this database over here? Reading from a database is so much slower than reading from memory. This is clearly the bottleneck when it comes to latency. So how could we improve this? If we need the rules to be stored persistently, we can't, prevent having a database. As these APIs are defined and we add rules to the database, we'll have to write to them, but in theory, rules won't be created super frequently, not nearly as frequently as we will be reading from the rules. So one thing that we could actually do here is have a middle layer in between the database and the rate limiter, and this will be our hash. So periodically, we will take rules that are written to the database and copy them to our cache. And it, of course, is going to be some in-memory cache because we want the reads to be as quickly as possible. So we will kind of replicate these rules to be in memory, but we also get the fact that they are persistent, but we also get quick reads. So we as developers, as we define rules or update rules, we need some type of background process that will also cache them. And for that, we can have, some type of worker that is responsible for doing that. Of course, a database can't directly write something. So we would read from the database and then periodically update the cache. We could do this pretty frequently to make sure that the rate limiter isn't reading stale rules. And like I said, we're not going to be updating the rules super frequently likely. So this should be good enough, and we can probably scale these horizontally as well if we really needed to. So with that, we have gone over a lot of the design considerations when designing a rate limiter. So next, let's design tinyURL or just any type of URL shortening service, something like Bitly or however you pronounce that. And I'm sure there's others, but we're mainly going to be focusing on the core functionality of a URL shortening service. So first, let's quickly go over the background, even though you might already be familiar with it. Given some type of long URL like this one, neatcode.io, courses, system design for beginners, we want a more short, user-friendly URL, something like this, tinyurl.com. And in this case, we have sort of a short string here. And when we actually open up this URL, it's going to redirect us automatically to the long URL. And of course, for this mapping to exist, we would have to create it. We would have to specify this is the input URL, give us a short URL, and this would be the output, and then we can use the short URL from there on. So now let's go over the functional requirements, which we already kind of started doing. We want to be able to map long URLs to short URLs, and then using those short URLs, we should be automatically redirected to the long URL. Obviously, this one should be relatively short. That's the whole purpose. So while it would be even more user-friendly for this part, this little path ID to actually be a words, like happy or something like that, we might not always be able to do that. We might need to have, just some jargon, some scrambled up characters here. So let's say the restriction for us is that we want this to be 8 characters to keep it user-friendly. And to make it simple, let's say we don't include the case where users are able to specify their own string, their own user-friendly string, because it's not too different for our design. Now, in theory, a user could also delete a URL, of course, only if they own it. So we need to keep track of the ownership of these URLs. But for simplicity, we won't consider the case where users can actually delete these, even though it doesn't really change our design too much. And let's say that our URLs actually do expire. Maybe by default it's a year. Every URL expires after a year, but maybe users can specify a longer time period that they want their URL to expire, maybe 5 years, maybe 10 years. So we do need to think about this in terms of a long-term mindset. We don't want to run out of resources is what I'm kind of getting at. Now, a last clarifying question would be to ask, what would happen if multiple users had the exact same long URL and they were trying to map it to a short URL? Should it always map to the same short URL? I mean, what difference would it make if a user is trying to shorten a URL, but there's already a shortened version of that? Why not just give them the same short URL? Well, remember, we do have this sort of concept of ownership. What if I set my URL to expire, but somebody else had the same long URL shortened to the same one, to this exact same one, and then this one expires? Well, another user might not have wanted that. They might have wanted their expiration to be, 5 years or something like that. So how about, even if the same long URL has already been shortened, we create a unique short URL every single time? I think that would be a good clarifying question to ask, because it definitely is going to affect the outcome of our design. Now, in terms of non-functional requirements, obviously we want this to be as available as possible and as fault tolerant as possible. So if components of our design end up failing, we do not want the entire system to shut down. And the point of a short URL is to make it more user-friendly. So we definitely don't want to add additional latency, because at that point you might as well stick with the long URL if the short URL is going to be so much slower. So let's try to get as minimal latency as possible. Now, continuing with non-functional requirements, let's talk about the scale that we're going to be dealing with. In the real world, with a URL shortener, what do you think we're going to be doing more, writes or reads? Well, a write in this case would be actually creating a short URL, and a read would basically be using a short URL and then, getting what the long URL it maps to is. So which one do you think is going to be more frequent? Well, obviously reads are going to be a lot more frequent. You're probably not going to create a short URL just to use it one time. That would mean a 1-to-1 ratio, but reads are probably going to be a lot more frequent. It could be arbitrary. You can kind of already guess this, but to clarify with your interviewer, maybe they say we're going to have a ratio of 1 to 100. So 100 reads for every write. Okay, well then how many URLs are we actually going to create? Well, this is a generic enough service that we could be dealing with a lot of short URLs. Let's say the number that your interviewer gives you is something like 1 billion short URLs created per month. Now that's a very large number, and the first thing that's going through my mind is, if we only have 8 characters here, are we going to run out of space? Well, to ensure that we don't, we should use as many digits or characters as possible for every single position. Let's say we can use digits from 0 through 9, we can use lowercase a through z, and we can use uppercase a through z. That gives us 62 characters to choose from. So 62 to the power of 8 is actually going to be a very, very large number. You can kind of already guess that. This would definitely be hard to calculate on the back of an envelope or in your head. But remember, kind of 60 squared is 3,600. So 60 squared to the power of 4 is going to be 62 to the power of 8. So, this number to the power of 4 is going to be a very large number. This just squared is going to be at least 9 million, I think, because 1,000 squared is 1 million, and then you have 3 squared as well. So 3,600 squared is going to be something like 1 million. And we're probably going a little too deep with this, but this squared is the same as this, because 60 squared is 3,600, which we then square and then square again. That's to the power of 4 essentially. So 1 million squared is roughly a trillion. So 1 trillion is quite a lot of possibilities we have with short URLs. If we're creating 1 billion per month, we're not going to run out for 12 billion per year. So we would have at least almost 100 years. So that's pretty dang good. We don't really have to worry about that, but you probably didn't need to go through this, deep down into the math. Just looking at this, you can kind of tell it's a pretty large number. Now, 1 billion writes per month, when we get that down to a day, let's say it's around 33 million writes per day, and you divide that by the number of seconds in a day, which let's say is roughly 100,000, we're going to end up with roughly, let's say, 330 writes per second, or just rounding to 300, I think should be good enough, because the difference between 300 and 400, not super great, but roughly 400 writes per second. Not a ton, but a pretty large amount. Now, if we have a ratio of 1 to 100 when we talk about writes to reads, if we have roughly, let's say the number was 300 writes per second, we're going to have 100 times more reads, so that's going to be 30,000 reads per second. So we definitely have a lot more reads, and this is actually quite a lot of reads. So we're going to need to be able to handle this scale and try to identify the bottlenecks. Now, when we talk about storage, the writes are clearly more important. If we have 1 billion writes per month, well, how many URLs are we storing per month? And this is kind of the base domain. It could be anything, but we probably don't need to store this for every single URL because clearly it's going to be the same. So we're really just going to be storing this. It's going to be 8 characters. So that's 8 bytes. So does that mean we have 8 billion bytes? That's how much we're storing. 8 billion is going to be 8 gigabytes. Well, we might need to store more than just this. We might need to store some more metadata. Of course, we're going to need to store the long URL. How many characters could that be? Probably on average, I would think 100 characters is going to be fine, but it could be a lot larger. It could be 1,000 characters if there's, some super long URLs. But let's keep the average case in mind. Let's say 100 bytes. So we have our total at about 108 bytes per user, but let's give us some more leeway because we might need to store additional metadata. We might need to store like the user ID and some other stuff. So per URL, we're going to give a big number, something like 1,000 bytes per URL. As we'll see though, most likely it would actually be significantly less than this on average. But in terms of total storage, if we have 1,000 bytes per URL and we have 1 billion URLs created per month, we're gonna have 1,000 times 1 billion. That's gonna be 1 trillion. 1 trillion bytes is a terabyte. That's where the T comes from. So a terabyte per month. This is definitely reasonable, a lot smaller than the scale of like social media networks. So we're actually not storing that much data when you actually think about it. A terabyte per month over the course of 10 years would end up being a petabyte, not the worst thing in the world. Now let's get into the high level design, and we actually already talked about some details, and sometimes your mind can go into the details before you even get to the high level design. I think that's fine. One thing on my mind is actually what type of storage solution would we want to use. We talked about how we have a large amount of data, but it's not super large. The big thing for us is actually the amount of reads that we're going to be doing. We're not going to be writing frequently, so how are we going to be able to handle this scale? Well, my mind immediately goes to we can use some type of NoSQL database since they are specifically designed to be able to handle a large amount of scale. Now, they don't come with the ACID properties, and they're definitely not relational, but we're not going to be storing a lot. At the very core, we're just going to be mapping a long URL to a short URL and storing them together. Maybe we'll also store additional metadata, something like the user ID and some other info, but it's not like we're going to be doing a bunch of joins and a bunch of complex queries. We don't need those ACID rules. We don't need atomic transactions. And actually with the base properties with a NoSQL, we have eventual consistency. So when we create a URL, it might be that somebody reads one of our database replicas, and maybe that database replica does not have the most up-to-date URL just yet. That's fine because we know eventually all our replicas will be consistent. It's not like we're going to be writing super frequently. Eventually the replica will have that up-to-date URL. It might take a few seconds, and that's perfectly fine. But after all the replicas have the URL, it will be working. It will be able to handle that scale. So this is sort of an obvious choice in my mind. And the main responsibility of this NoSQL database is going to be to store those URLs. Now, the main user scenarios we're going to be doing is a user is going to possibly create a URL. They're going to hit some server, and suppose we have some type of way of generating a URL. So let's say we have another service over here, URL generator. This is very high level so far, but given that URL generator, we will from the server write to the database, and it may not be a single node database. Of course, there could be replicas and it could be distributed and all that. And that would be the scenario where a user is writing or creating a small URL given a long URL. And for reading, of course, they are going to hit the server, and given some short URL, we want to find in the database what is the long URL and then return that to the user, and then the user will be redirected to that long URL. Now, obviously, this is very, very high level, but I personally think it's good to kind of just go over a few basic things just to make sure you're on the right track with your interviewer, though some people would prefer to kind of delve into the details a bit more on like the URL generator and all that. One more thing I will say about the high-level design is, since we know we're going to be doing things very read heavy, of course we want the generated tiny URLs to be persisted, but it's probably good for us to have some sort of caching layer in between. So we would first hit the cache and see if the tiny URL is there, because most likely there's going to be a few tiny URLs that are used a lot more frequently than others. So having that subset of URLs here will create a much better user performance, and it will speed the redirect up by a lot. And this cache should of course be an in-memory cache, because that's kind of the whole point of making it faster than reading from disk on our database. Okay, so now let's spend a little more time and actually go into some of the details, because we've been pretty hand-wavy at this point. We haven't talked about what the request would look like to the server, and we especially have not talked about how the URLs will be generated. That's kind of the core of this entire problem. And we'll talk about how to scale this, but there's actually a few other points that are more important for this problem than the scale. First, I want to quickly mention, for the caching that we have, what type of algorithm could we have, and what size would the cache actually be? Well, we talked about how 1 terabyte of URLs will be created per month. Now, of course, the reads will be 1,000 times that, but that doesn't mean that we're gonna have that many unique URLs. That doesn't mean we need a petabyte of data for the amount of URLs that are gonna be read per month or in some type of time period. So I think a reasonable size for our cache would be something like 256 gigabytes. That is actually reasonable for memory, though it might be pretty expensive, but for, you know, a system like this, it's not the end of the world. Our cache could be distributed. We could implement sharding, and of course, so that receives the response, they'll immediately make a network request. Technically, it would be the long U. It gets kind of math heavy, so that we can say that problem of mentioned that we long URL problem. I think what makes this problem URLs, and of course the long URL that they want to store, and of course the key, aka the short URL that they want, and